Okay, so, math. So this is the basic idea. If we talk about an electric field, okay, if we talk about an electric field, concept zero is that, whoa, I hope I didn't just kick the bucket. Concept zero is that this line here is supposed to represent parallel plates like this. Okay? And the notion is, and this is what we're going to test with the lab that I just handed out, okay, is that the electric field in between these is uniform. Now what you're going to discover is that, especially because these guys are spaced out pretty far, that actually these field lines kind of curve out like this. Okay, the ones in the middle are really pretty parallel, but out near the edges they actually curve out like that. Okay, but the notion is that we can represent electric field with arrows that point in the direction that positive charge would start to move, right? So it's always what would positive charge do, and for a particular location, if you just pick that location, it's not the path that the charge would take if you released it, but it's where it would start moving if you were to put it there, right? It's the direction it would start to go. Does that make sense? Yeah, but because it has inertia, its actual path is actually fairly complicated. Okay, so if it's a non-uniform field. But anyway, a positive charge, of course, has a force in the direction of the electric field. That's the definition of it. A negative charge would have a force opposite the direction of that, right? And then we can talk about, well, let's see, if we had a positive and a negative. This is called, by the way, a dipole, right? Because it's got two poles, right? It's got positive and negative like that. In a dipole like this, if you put a point right there, it would start to move, of course, tangent to the field lines. Yeah? Does that make sense? Right? And so this is our fields like that. And then if we had two positives like that, they would go away from each other, right? And then I've got this, this thing, and I'll pull this out. This is actually a magnetic field that I'm going to show you, but it's the same thing for electric fields. And then when we get to talking about magnetic fields, I'm going to say this is a magnetic field, that we're talking about here. All right, here we go. Do we have a bad bulb? Yes. All right. There we go. It's like that projector is the varsity projector in the school. It actually has like a spare bulb built into it, and I can just slide the thing over if the bulb burns out enough to like take it apart and, yeah? Huh? There we go. All right. Let's focus on this. There we go. That's kind of neat, isn't it? And then I'm going to take a single bar magnet, and let's put this guy on top of the bar magnet. And you can see that the little filings tend to line up like compass needles to the magnetic field in this case. And one end of this is north and one end of it is south. Yeah, does that make sense? And one thing you can see is that the North Pole and the South Pole are not actually at the ends of the magnets. They're somewhere kind of like in the middle here, isn't it? Like that's the actual thing is there and that's the actual thing there, right? Okay. That's kind of good. A little applause for that. All right. And then we can also do the picture on the overhead of the positives. Let's try this. I'm going to get two North Pole magnets. Like, are you a North Pole? No. It's actually bad to do. It's like, I don't want to go. All right. Here we go. There we go. And that's kind of like the picture on the right side. So a little applause for that. Just a burst. Yeah! There you go. Okay. So anyway, then the question is, of course, what would a positive charge do here? Well, this implies that there's not actually a lot of electric field in this case right there. In fact, a positive charge here could be precariously balanced in the middle like that. Okay. Anyway. Okay, let's hit the right arrow, see what it shows us. Demo the bar magnet, right? Here's an interesting thing. If I put a positive charge, an isolated positive charge, and I surround it with a sphere of metal. And I surround it with a sphere of metal. Are you picturing this? One might think, we could shield the rest of the world from that positive charge. They would not know it's there. But a strange thing happens, right? Remember that the inside of this conductor, it's a conductor, the charge can move. And so if you put a positive charge inside the conductor, it sucks the negative charge on that conductor, moves to the inside of the conductor, yeah? Leaving the outside of the conductor positively charged. So out here, we don't even know that that's there. That's kind of crazy, isn't it? So it induces a charge. Now, let's think about inside this conductor. Let's put ourselves inside that conductor. What would positive charge do there? What would it do? Well, it would move away from this positive one, wouldn't it? But look at that. Look, there's a localized charge distribution. There's an induced charge on the conductor, isn't there? And so it would tend to move away from this, but equally it would tend to move away from the outside of the conductor, so it would move toward the middle, wouldn't it? Do you suppose the charge will move on the conductor so that there is no electric field inside the conductor? Yeah, because imagine if there were an electric field, wouldn't the charge move? Were there an electric field inside a conductor, charge would move. When would it stop moving? Think about it. When does it stop moving? Remember, it can move. Let's just assume our model for conductors that there's no resistance to motion of the electrons. So when does the charge stop moving? When the electric field ceases to exist. Yes, if there exists an electric field, it's like if it's not zero, it's not at the top, right? It's the same concept, only it's harder to think about, right? If there's an electric field, charge will move. Yes? The charge will move in such a way that it cancels the electric field, correct? Look at this example here, right? The electric field due to this guy is away from that guy. Yes? Okay? The electric field due to the induced charge is toward that guy, yes? It will move until it cancels out the electric field. Okay, so for situations that have long enough time for the charge to move, we're talking about static charge distributions. We're not talking about things that are changing, at a megahertz frequency or something like that. That gets more complicated, right? We're talking about things that are just static. This guy just sits there and it's positive for a long time, a couple seconds, right? The charge is going to move until it cancels out the electric field. Okay, let's do a simpler example of this. Okay. Here's we make a little box. We've got a box, and we put a box inside. These are parallel plates, and these parallel plates are close together. When they're close together, the field is quite uniform, although here they show it being a little non-uniform near the edges. Again, your lab will show you that. Now look at the box. It's a box inside an electric field. Now, and of course, the box is going to have a positive charge on this side. Yeah? Negative charge on this side. Yeah? Look at that induced charge. This electric field is this way. The induced charge creates an electric field that is this way. Do you suppose it cancels? Does it cancel? Yeah, it cancels exactly. Because if it didn't cancel, there'd be an electric field and charge would keep moving until it canceled. Right? Kind of a crazy thing. This is in your guys' way, isn't it? Un poco. Un poco. Perdón, señor. Stay. All right. So that's a crazy thing, right? So you can, in theory, cell phones communicate with electromagnetic fields, don't they? Yeah? Part of that's electric. So if you put your cell phone here, and it's entirely enclosed, you shouldn't be able to reach it, should you? I need to get at one of the other physics teachers has this like a wire cage, right? And it can't go through fine metal mesh, right? He's got a little wire cage, and he puts a cell phone in there, and then he has the kids try to call it. This is kind of fun, isn't it? And of course,